A received EVPN route is a control plane fact. A forwarded packet is the result of several independent owners accepting and translating that fact. In a SONiC and FRR system, configuration intent, BGP, Zebra, the Linux kernel, synchronization daemons, orchestration, SAI, and the ASIC each hold a different representation. The rejected assumption is that show BGP proves hardware forwarding. It does not. The core learning is this: every layer makes a separate claim, and trustworthy operations follow one object through every ownership boundary until a packet confirms the programmed action. Here is our agenda. We shall begin with authoritative configuration intent. We shall inspect FRRB, GP receipt, selection, and export. We shall cross the Zebra boundary into routes, neighbors, forwarding database entries, and next hops. We shall identify the Linux bridge, VRF, VXLAN, and netlink objects FRR depends upon. We shall then follow SONiC synchronization and orchestration through application and ASIC databases into SAI and hardware. Finally, we shall examine restart and state divergence, then prove one route end-to-end. The objective is ownership and evidence, not memorizing daemon names. Consider one remote Type 2 route. BGP stores an NLRI, path attributes, route targets, ESI, MAC, IP, and VTEP next hop. Import policy may create a selected MAC VRF path. Zebra translates that path into a remote MAC, neighbor, tunnel, or next hop request. The kernel or platform adapter represents it differently again. SONiC orchestration may create an ASIC forwarding database entry and tunnel next hop. These objects have different keys, lifetimes, and owners. A successful upstream step can coexist with a failed downstream translation. Record the correlation fields at each boundary. Before troubleshooting dynamic state, identify who owns configuration. SONiC commonly stores running intent in config.db, Redis database 4, while a persisted config.dbj SON file may seed the next boot. FRR commonly uses its integrated configuration file, a boot script, live Redis command, generated JSON, and manual VTYSH change can all express different values. The system may work until restart reveals the losing writer. Define one owner per object class, render from version control, validate the target image's schema, and make save or reload an explicit workflow. Compare running, persisted, and generated intent before changing the network. FRRBGPD owns BGP protocol state. It can prove that the L2 VPNE VPN family was negotiated, an NLRI was received, attributes were decoded, policy imported it, and a best path was selected. Per VNI and Ethernet segment views expose additional derived control state. This evidence is essential but bounded. BGPD does not directly observe whether the Linux bridge accepted an FDB entry, SONiC Orchagent created the correct SAI object, or the ASIC enforced a split horizon filter. Use structured BGP output and capture the exact route key, then cross into the next owner instead of declaring completion. Zebra is FRR's routing information and forwarding plane coordination layer. It learns interface and VRF topology, receives selected routes from protocol daemons, resolves next hops, and sends forwarding requests through Netlink, FPM, or platform integrations. EVPN depends heavily on this join. A VNI may remain inactive because the corresponding Linux interface is absent. A remote route may remain unresolved because its VTEP next hop lacks an underlay route. A multi-homing path may require a next hop group the downstream platform cannot realize. Inspect Zebra's view, interface state, and resolution result before blaming BGP or the ASIC. On a Linux-based realization, the network device graph is part of EVPN configuration. A bridge and VLAN membership represent MAC-VRFs. An SVI binds a subnet to a VRF for routing or neighbor suppression. A VXLAN device supplies the local tunnel endpoint and VNI mapping. Current FRR documentation recommends the single VXLAN device model with external and VNI filter behavior for modern deployments, but target kernels differ. FRR learns this topology through Netlink. A wrong master relationship, learning flag, VNI mapping, or local address can make correct BGP state unusable. A Linux bridge may learn local source MACs dynamically, while FRR or a platform agent programs remote entries learned through EVPN. Neighbor entries can likewise be local, remote, static, or externally learned. These origins affect aging, mobility, and cleanup. A remote entry that appears dynamic may disappear independently of the control plane. A locally learned entry incorrectly marked permanent may survive a move. Inspect flags, device, VNI, destination, VTEP, VRF, and protocol origin. Then withdraw the EVPN route and verify that only the remote object disappears. Kernel presence is still not proof that hardware contains an equivalent entry. Sonic decomposes state distribution into database contracts. FPM sync and related daemons translate routing, neighbor, and forwarding database events into application database tables. EVPN multi-homing designs add state for DF decisions, split horizon, backup next hop groups, and VXLAN forwarding. Exact table names and schemas are release sensitive. A high-level design describes intent, not necessarily shipped code. Inspect the target images tables and component versions. Correlate one route or MAC through the actual application row. And verify that deletion propagates. Do not automate against a mutable HLD name without live schema evidence. Orcagent consumes application intent, validates dependencies, and creates SAI objects represented in ASI CDB. Depending on the service, these may include tunnel next hops, forwarding database entries, router interfaces, routes, next hop groups, and filtering objects. Syncd invokes the vendor SAI implementation, which programs the ASIC. A row in ASICDB proves a requested object model, not necessarily successful hardware behavior. Inspect orchestration errors. SAI return status, resource availability, and hardware counters. Finally, send a packet that exercises the exact entry, including an alternate path and negative filter when relevant. Divergence is diagnostic when observations are ordered. If BGP has the root but Zebra does not, inspect import and resolution. If Zebra has it but the expected application row is absent, inspect FPM and synchronization. If application intent exists but ASICDB does not, inspect orchagent dependencies and errors. If ASICDB exists but the packet fails, inspect SAI, hardware resources, counters, and encap details. The reverse direction matters too. After withdrawal, a stale kernel or ASIC object identifies cleanup failure. Record timestamps and keys, so an asynchronous delay is not mistaken for permanent divergence. Restart changes ownership, while state may remain. BGP graceful restart can retain peer roots when forwarding is assumed to continue. Sonic warm restart may retain database or hardware objects while components rebuild their view. Object identifiers, next hop groups, and multi-homing filters must reconcile with the retained data plane. If a component restarts without knowing which objects it owns, duplicates or stale entries can survive. Test BGPD, Zebra, synchronization, orchagent, cold boot, and any claimed warm reboot separately. A clean final root table is insufficient. Compare packet loss, object continuity, replay, cleanup, and persisted configuration across the event. Choose one remote MAC and IP binding, one Type 5 prefix, one BUM member, and one multi-homing path. For each object, record the configuration source, BGPNLRI, and attributes selected VRF and VNI, Zebra resolution, Linux state, application, and ASIC database keys, and representative packet. Then withdraw the origin and repeat the chain in reverse. Negative proof requires no unrelated tenant object to change and no stale tunnel path to remain. This evidence bundle reveals the first owner that disagrees and can be repeated after restart, upgrade, or platform change. The core learning is this: a BGP root, a kernel object, and an ASIC entry are distinct claims owned by different components. Configuration declares intent. BGPD owns protocol truth. Zebra resolves it against interface and next hop state. Linux or a platform adapter represents forwarding objects. Sonic synchronization and orchestration translate them into SAI requests and hardware state. The packet is the final behavioral evidence. Troubleshoot in that order and stop at the first missing translation. Then, withdraw the source and prove cleanup in reverse. Never use one layer's success as a substitute for observing the layer that actually failed.